million floating point operations. Gigaflops then became teraflops, which is 1,000 gigaflops, and teraflops has become petaflops, and people expect that trend to continue. They're doing it by throwing more and more processors at it, or clusters. Remember, the US government helped fund the technologies that you could figure out how to connect all these things, what works, what doesn't work, what's the technology. And so there is a expectation in the industry that in the year 2018 we'll actually reach an exaflop, which is 1,000 petaflops. Even I have trouble figuring out, well, how many quadrillion, 1,000 quadrillion floating point operation? Even I stumble upon those. It's a lot. And people will say, what do you really need it for? Well, I'll tell you all about it. What do we need it for? Here's the pictures. The first gigaflop system, so we started with the Cray 1, a megaflop, and so quickly they learned how to build better. The Cray YMP, which had 8 processors, and the Cray 2, which had 16 processors. That's the Cray YMP, and it actually had a Y shape. In the center up there was all the I/O modules and the CPU modules. Half were in this, half in this, so it formed the shape of a Y. That's the Cray 2, which had the classical shape. This was designed by a student of Seymour Cray, so he kind of split from the design a little bit. This Seymour, he designed it, and if you look closely, you can see water columns, floor inert columns at the back, where there are pumps, and you would see the module sitting with the electrical wires going through it, and once in a while, you'd actually see a few bubbles rising to the top. Now, you all know me very well from many, many, many years. I cannot resist throwing in my own brand of humor here. So one day we are looking at this and we see this once in a while, a little bubble rise. These things are immersed. So I say to the guy next to me, he's in Germany, he's still around there, works in Switzerland now. I said, you know what? This gives new meaning to the term floating point error. Hey, I warned you. But that's an original. So it was really fun to watch these bubbles floating up, and people would build, like large companies would buy these machines. They'd build this great display and walk all the shareholders through it. So that's the Cray 2 out there. The first teraflop system was, that initiative ASCII, red, white, blue. So that one was built by Intel. It had 9,000 Pentium Pros in it. The joke at that time was that it takes a few hours for Windows to boot up. They never ran Windows lightweight. They wrote their own operating system called MOS, M-O-S, Massive Operating System at Sandia. So that they ran code, and actually the real boxes are in white out here. This was the power supply. This wasn't the real box, but they called red because that's what the specification said. The machines could be any color, but to distinguish, so this was 9,000 processors. Then the first petaflop system was just 5 years ago, 2008. Yes, it was called the Roadrunner. It was supplied to Los Alamos National Lab, and it was built by IBM, and they used the first hybrid chip. They built a chip for the Sony PS, first PS, that was based on their own processor called the Cell. So that was like a GPU. So it was a GPU with regular processors, their own power chip, and that was called Roadrunner, and that broke the petaflop. Just a few months ago, they retired that system. So what is amazing that even breakthrough systems in 2008 are very quickly approaching retirement, because now that was the only petaflop system in 2008. There are now 37 petaflop systems available. So technology adoption is very fast. And the first exaflop system, I left it as a question mark. Even though they're all predicting 2008, I have my own doubts. And I'll tell you why. You've all heard of the word sequester. Well, who's been funding, now the commercial adopters or buyers of HPC or supercomputing, but they generally wait on the sidelines, let the government do its stuff, let the industry figure it out, and when they make several of these, we'll buy it. the government has been the funding for all of these, and because they're scaling back, everyone else has to scale back. So that's doubt number one, if it'll happen in 2018. However, I'll also say that, there's something called innovation. They come up with clever ideas. For example, now they have three-dimensional stacked CPUs. When they run out of real estate in silicon, they've got that technology. They're shrinking it to almost, I believe, 14, 11, and 8 nanometers is the bar. Beyond that, there's so much leakage at the semiconductor. So who knows what sort of innovation they'll come up with. And this is also caused the people, and there's a lot of international efforts. The total funding, even with the sequester, is about $128 million by the US government towards the next exaflop system. They're spending time figuring out, we can't use the programs of old, we've got to think different, have parallel programming languages. By the way, the operating system will be Linux, so you can all be assured that there'll be plenty of jobs there. But what I said is, because it's going to have at least 1 million cores, how do you make all of them sing in harmony? That's how you're going to get that speed, if they're all running at the same speed on different parts of the code. So they're trying to rethink, and if one of them fails, does the entire program get thrown out? We've got to make sure there's reliability restart built in at the software level, firmware level, hardware level. So we've got a big challenge on our hands. That's why I think it might take a little longer, but let's see what happens here.
What year was Red?
I believe it was mid-90s it was.
So
I
like
don't know the
95?
exact. Yeah,
So
95,
it took like 13
96.
years then to get to the next level.
Yeah. It's getting faster and faster. There's a chart, in fact, that's the next slide here. In 1993, people, these four gentlemen got together and said, how do we measure these? They came up with a linear algebra package called LinPack. And they said, run this, and what's the biggest equation you can solve? And when you get to that biggest equation, what is the clock speed? What is the speed at which output results are produced? They had a way of measuring it. So from that, they can compute how many gigaflops or megaflops it had. So 1993 was when they came up with the LinPack benchmark, and they created a top 500 list because these are top 500 computers in the entire world that can run these and make the cut for that list. And I'm sure you've seen in the last couple of weeks, there's been big noise about China wanting to push the US off the top of that list. By the way, I'll show some graphs on it, but the bulk of the systems are in the US. There's a few in Europe. Asia Pacific was non-existent, but they're now coming on real strong, and China's trying to become a very big player in that. There's very clear economic outcomes from having powerful machines. You can use it to design, and I'll talk about that, better products, products that you just cannot do any conventional way. So it gives you an economic advantage or edge. There have been people who then took that original 500 list and they came up with a power efficiency list. These are all floating points. Some people said, we don't do floating point, we do a lot of searching. So we should have our own algorithm that can measure the powerful computer is powerful at searching. What's good at floating point may be terrible at, comparing strings, for example. So, and there's a few other variations that have come out, but by and large, everyone recognizes this as being, the official recognition of the most powerful machines in the world. You can actually go to top500.org, and you can find all of these charts. I don't apologize for the graininess of this. All of it is online, but this is what it looks like, and they've been tracking it. This purple is the top machine. This is an average of all the 500, and this is the small, power of the last machine on that 500 list. The interesting thing is that a few years ago, what was the top machine won't even make the cut this year.
The China one was out yesterday, took number one.
Well, they are going to announce it at a conference that takes place this week. starting.
They ran it at 90% capacity. I guess the articles were out yesterday. They ran it
Yeah,
at
the
90.
article is out,
Yeah.
but these gentlemen here,
They want it.
Mr. Dongara, Eric Strohmeyer, Hans Muir, and Horst Simon. Eric Strohmeyer and Horst Simon at our Lawrence Berkeley lab. Jack Dongara is at the University of Tennessee, and Hans Muir is out in Europe. They have to officially certify the results, and they'll officially release the list. It is released in June and November, twice a year, and so we'll find out. I have no doubt that they will push the US off the list. They actually secretly built a machine that could do 100 petaflops. It will actually, 100 is a theoretical maximum. They'll probably get only about half of that, so about 50 petaflops. It has to work on a real application, the lid pack, so that's what I expect it will come out with. But it's impressive performance, and they're spending a lot of money. After all, it's money that we're paying them, to build it. All right, now let's get on to software. That's enough about hardware, technology, and exotic stuff. By the way, while we're on the topic of Cray, we used to work on the console of a $10 million machine, and of course we had regular PC or laptops. So we all came up with the sticker that my other PC is a Cray. And I actually have some left over. What I'd like to do is pass it around. Those of you who like it can keep one and stick it on. If I have more, I'll give it to you.
Can we make
So
that
do share.
can we make that the thing that win? So we have a drawing at the end of the thing. Can we do that?
Okay.
Make one of at least one of
Well,
those?
there's plenty of this. We'll have something else for a drawing.
Oh, okay.
Wasn't Dell
Yes.
selling a baby Cray?
Who?
Wasn't Dell Computer selling a little baby Cray?
Oh, many of them claim to sell a baby Cray, but it's not the Cray of old. Today, even Cray is now selling clusters. They've done away with vectors. And now we have several companies out there that sell baby supercomputers, and they just call clusters these days. But the most famous of them was Convex Computer out of Richardson, Texas. They were bought by Hewlett-Packard. And they actually called their stuff baby Crays or Crayettes, and they sold them. And there are a few other companies. So, yes.
The one I remember reading about it was Cray, it was sold by Dell, it was single user.
Okay. What you're talking about is actually a workstation on steroids.
Yeah.
Yes, and in fact, Cray sells them, and I really call them a workstation on steroids. It had Dell manufacture it for them, but Dell didn't put their label on it. And Bull in Europe also built for them according to the spec. It came with InfiniBand, 64 cores, and everything on a workstation box. So you could run code on it, and actually could be used as a developer workstation, and it could run on the larger machines. And, by the way, they run Linux because they're like clusters anyway. But in those days, remember, you're talking about special purpose hardware, so they had to write operating systems for them. And in those days, operating system developers, they could command any kind of salary they wanted. The earlier one that Mr. Seymour did, the best he gave them was an assembly loader program. 8-line or 20-line assembly load program, that's it, that's what you got. Then Los Alamos wrote CTSS, Cray Time Sharing System, and then Livermore wrote their own version called LTSS. And Cray recognized that, we've got too many of these to support this, we've got to know this, let's create our own. So they called it Cray Operating System. And it looked like DOS in those days, to tell you the truth. There were like 10 commands, and that was it. Then they finally saw the light in, I'd say, middle of 85, 86. And so they hired a bunch of people from Bell Labs out in New Jersey, relocated them to Minneapolis, and they ported regular System 5, AT&T System 5 to Cray and called it Unicose. And they added a few BSD elements to it, but that's what they supported. Then when they came out with their massively parallel processors, the Cray T3, the one with the Taurus three-dimensional architecture, they decided that we don't need all of the things that Unix has. They stripped it down to a microkernel, called it Taurus, and ran it. And then around this time, I would say early 90s, the first Beowulf cluster appeared. And we all know its architecture, but in those days it was called Beowulf. The two architects of those, I believe Beowulf is some character from Nordic
Yes.
literature, stuff like that. And so they were fans of that, and they gave names from that literature to different parts of the architecture. And of course they ported Linux to it, and that's how it worked. But what was the motivation behind that? The motivation was very clear, that microprocessors, if you look, they started becoming faster and faster, and these were the regular Cray processors. If you look at the speed wasn't terribly improving year on year. It was very minor. But these, they said it's going to intersect somewhere around the year 1995. So around 92, 93, they started making efforts to build stuff out of microprocessors, or they call killer micros. And I'm still looking for that cartoon Guy Glass almost he presented, where he showed these little chips with spider-like legs, and they're all kind of coming from all around, and there's a Cray in the center, and they're climbing up and eating it. Kind of reminded me of an episode of Stargate, something like that. But I'm looking for that, so when I find it, I'll add it to this slide presentation. And then, of course, there were people who say, well, yeah, you can build special purpose computers with microprocessors, but why don't we just use workstations? They're connected with the network. They're already functional. We can do that. So the two converged together, and they actually created the first Beowulf cluster with 133 nodes, regular hardware. And this was built at NASA Caltech. And these were the two authors. Don Becker went and started his own company called Penguin Computing, if you've heard of it. And Thomas Sterling, he then moved from there to Louisiana State University. And last year, November, he took a permanent position at Indiana University. So he's now pretty close to us. And there he directs the high performance computing program. That's what it looked like, the very first one. As you can see, it's a whole bunch of repurposed workstations. You can recognize some of these boxes here, some desktops, power supplies, some boxes, everything kind of mishmashed together, and that was your first Beowulf cluster, and it actually worked. There was a prototype before that, that was at Caltech, and that looks like really it was in a lab, kind of Frankenstein lab picture. And then a few other people did it with more neatly arranged workstation. But the concept, everyone bought into it, and today clusters are de facto. They're the bulk of high-performance computing today, and then the others are the special stuff. He actually has a book out there, Beowulf Cluster Computing with Linux, and that is the Bible by which most people today build clusters. Even your Dells, your HPs, IBM, everyone builds clusters. You can buy from at least 100 different vendors clusters, and you can have your own supercomputer. And there it is. First he was at Caltech, NASA, then LSU, and now he's at Indiana University. So I meet him once a year. He's a very interesting fellow, jokes a great deal, and he also shares the same opinion that he doesn't think exaflop will happen, but he says he's happy to be proven wrong. And then, of course, to make clusters more popular, many in the open source community, some of these folks, they all contributed different libraries, threads, OpenMP. Many of the software came from all over the place. Obviously, everyone knows the cluster feature is great. It's open source, it's low cost. You can add more nodes to the cluster. You can add more storage to the cluster. It's elastic. The whole idea is that you spread the work around equally. There's software that'll chop it up for you and send it across. Slurm is a package that you can use to manage these clusters. And of course, they've now improved things so that when there are node failures, they can recover from it. And so there's also all these Linux operating systems to try and present maybe a single operating view. And all of these are still very, very active. Skilled is part of what is now Penguin Computing. Open is a single system image based on Linux. There's G-Lite, then LVS. Has anyone worked with LVS? Linux Virtual Server. So it's kind of like, you know, your VMs, but independently pioneered. Then of course we have Linux HA, the heartbeat, so that they could detect a node failure and quickly produce it. And then there's one Ubuntu based called ABC Linux. And this is by no means an exhaustive list. There's plenty of work out there that people are doing. Just a few months ago, we heard from the Ceph folks. Ceph is very popular in high performance computing when it comes to clusters. But of course, the big guys, they use Lustre. And of course, recently we've started seeing Hadoop and GlusterFS. Red Hat has their own global file system. So plenty of choices out there. But all of this technology, I believe both Linux and open source has helped high performance computing, and high performance computing has helped Linux because they need to run on thousands of nodes, so the software is worthwhile investments they can do. This is what a typical stack would look like if you walked into any shop that ran a cluster, high performance cluster. It would have all of these elements. OFED is Open Fabrics Enterprise Distribution. They decided that, you know, the way we interconnect these, we can't be tied to one vendor, so they actually have a vendor-neutral distribution. It works on 10 gig, and it includes TCP offload engines, and the network here could be InfiniBand, proprietary network, or regular 10 gig. And then it supports all of these file systems. You see Ceph up there. Lustre is pretty popular. This is IBM GPFS, which has been ported to Linux, and we all know about parallel NFS. XFS came from SGI, they contributed the source. And then of course, MPage and OpenMPI, they're important for the application to make the MPI calling interface so that they could work on any Linux-based hardware. And this doesn't mean x86. You have Linux running on IBM Power chips. You have Linux running on ARM. You could make it out of anything. As a matter of fact, just a few days ago, there was out from Boise State University a student who used a bunch of Raspberry Pis and built a cluster for less than $1,000, and he got some great speed up. I was so impressed with it that I took the trouble of printing it out, and I wanted to share it with all of you. Could you pass this here? And I'll give you the URL later in the slides. But it's basically kind of becoming, what do you say, far more democratic. Anyone can do it, whereas HPC used to be the domain of people behind closed doors who wore white coats and put on these little booties over their shoes and hats and entered the room. No longer. You can do it out of your basement. Yeah.
You used Arch Linux.
Okay, well, let's look at the history. Linux didn't happen overnight. This is a little bit of the history of the architecture. And the architecture here, was it single processor high performance or multiple processor or a cluster? There are really, 3 or 4 different kinds. So the single processor, this was the Cray days. As you can see, around 1996, 97, Cray started going out of style. It was gone. The yellow is symmetric multiprocessors. Those are like single giant memory with a lot of cores connecting it, like your classical RISC architectures or HP or DEC or IBM. So they sort of took over from the Crays, but you can see that around 2005 they've flatlined and gone. And around 2003 or so, this blue out here is the cluster technology. As you can see, they're now easily, 80% of the entire HPC space. And this purple out here is massively parallel processors. They're using standard chips, maybe stripped down a little bit, but they're put together with special interconnect, and they put thousands of them together. That's why massively parallel processors. They dominated for a little while, but now they only share about 20% of the entire space. But I will say they're still the fastest. This might be cheaper and you can solve the same problem. Those are more expensive, but you get bigger speeds from it. So they're kind of comfortably now sitting on that perch where you have mainstream, kind of like sedans and sports cars. You know, we're in Motor Town, so we got to use that analogy. Yes?
If you were to try to do a comparison of cost, if you were to include cost in that group, that graph,
Yeah.
would you get, because the MPP stuff's probably really expensive.
Yes.
Where the cluster stuff is probably really cheap.
Yeah, so let me put it this way, the entry level for a cluster is very low. But you get far more performance from a massively parallel, but the entry cost is high.
Right, so performance per dollar, I'm curious which way it would
The
flip.
MPPs are better in
Really?
performance
So-
per dollar, but the entry cost is very high.
Yeah.
So, you know, it's a trade-off, and many people are quite comfortable with clusters. Not every problem demands the biggest and most powerful hammer. So,
Just the big nails.
yeah. Let's see. Okay, and then I wanted to show, well, we now know what's the ratio of clusters versus everybody else. Let's look at the ratio of what operating systems versus everyone else. Well, the pink one here is Linux, so as you can see, well, they basically took over, say, around maybe, 1998 or so they started, and then it just exploded. Your light blue is your classical Linux, you know, that we know. They'll still be around.
You mean
But
Unix?
Unix is like System 5 with BSD. That's what I mean by Unix. And you know what? There's actually this tiny little sliver here is Windows here.
That's the way.
Yeah, that's the Windows one.
How did they get in there at all?
Well, nowadays they don't sell Windows HPC, it's called Windows Azure, from what I'm told by the group that was the old Windows HPC. They've gone to cloud, that's all that they do. This is actually more a distribution of what kind of Linux. Like you had Super UX from one of the Japanese vendors, Solaris, IRIX, SGI, classical Unix. So this is a distribution amongst them. And the Linux, as you can see, it's all yellow. They basically picked up and they've now dominated. And you'll still have these microkernels or Unix-based, but they're running on the MPP. Because they've invested, ported, they're going to stay there. They determined that if they had to port Linux, they'd have to dump 90% of it in order to run. And so why repeat that effort so they can stay with their original port, which is already optimized to begin with, and their derivatives of Unix. And for those of you who like to know how much is CentOS, how much is SLAS, and Red Hat and all that, here's one slide that talks about it. As you can see, this is CentOS version, the blue one. That's actually beginning to grow a little bit. And then the SLES is the pink one. Surprisingly, it should be more, but it stayed very static here. And let's see. Okay, but the real question is, out of all the top 500 most powerful computers in the world, if we were to rank them by their fastest possible theoretical speed, it's very clear that this is actually one physical system, another physical. This is what is called a tree map. These would be all the non-Linux, and these is everyone else. The most important thing is that the size of this corresponds to the actual performance. And Linux wins by a big, big margin. And so those few MPPs that do have custom OSs, they'll also disappear after a while.
So you think in time the MPPs will be gone, completely replaced by
The MPP architecture will be there, they'll be now running Linux. And MPP will also start shrinking because clusters are just now have a much more compelling case. Because of their volume and market share, new technologies are appearing in Linux and clusters first. So basically it has
Has
two
every-
things going for it.
Has everyone seen this?
Yeah, just keep passing it around
There's a
here.
couple of them.
Let's start getting towards the end of, this whole thing. Currently, and I think this is going to be out of date probably within 48 hours, the current number one system has more than 500,000 cores in it. It's located at Oak Ridge, and it's an actual Cray X model K7. It's called Titan. It actually has GPGPUs in it, and I brought a sample of that GPGPU in